we look at this. I show you this calendar again. And, I wonder what's the date for the final? You guys know? Monday, December or this? Okay.
5 p.m. 5 p.m. Now you're 5 p.m. Yes, it's the final one. Really, I check it.
1st December is a Saturday. Yeah, 3rd, that's Monday. Okay. That's good, it's not the first day. Before this module is always the first day of the examination week. Before it's somewhere here, always the first week. You know, for reading week, we cannot do anything. But you can do something. But for me, I cannot do anything for you. And for week 13, this for 15th, right? 15th November we have the last lecture. It's a revision. And actually, I just show you like 1 or 2 slides, give another 2 or 3 examples. That's on this day, 15th of November. And 13th of November and 8th of November, that's 2 lecture time for you guys to present. That's for projects. 2 hours, 5 groups. We set 2 lecture times for the project presentation. Actually, it's not a real project. I just give you some questions. You just show your class and how to solve those questions. Of course, if you have your own spectrum, no problem. That's even better. Okay, this is I will write it down just in case we. Final exam is the 3rd of December, right? Then 15 November is a revision. Then 13 and 8 and 13 November we save for projects. Then 6 is a holiday, right? Then we have 1, 2, 3, 4, 5, 6 lectures time left. That's more than enough. So actually from this time on this week, Monday on the week 11, I will give out for the project questions. You have more than enough time, okay? And on Tuesday we have a lecture, but for this 1st of November, you want time to prepare or you want me to talk? It depends on you guys. How many want 1st of November lecture time off to prepare for your own slides, for your project? How many? Like for the first of November, that's a Thursday, and you want that day off, then you can have more time to prepare for your project. And then we have lecture time. This. We have 5 lecture time left. That's more than enough. And if you guys agree, we have 1st of November off for your preparation for the project. Maybe you vote again for once. I will just make sure I give it off or not. If you want, please raise your hand. Okay, in that case, we have you write it down for 1st of November, no lecture. In the afternoon, no lecture, and you spend time to prepare for your presentation. You just prepare your projects very carefully. And last year, every year is very rare if you have a wrong answer. But last year there is one group they had wrong answer. But that happens. Sorry, that did happen. And of course, for that spectra, it's not so clean. But this year, maybe you find your own spectra to work on, then you can have a clean spectra. But for me, every year I struggled to get spectra for you guys to analyze. But anyway, I have to give you, if you don't have your own project, then we have 5 lecture time, no problem. And by today we will finish all. And we have 4 lecture times, give examples and also tutorial examples. We have more practice. That's why don't worry about this 2D technique. It's believe me, it's much easier than 1D. And this is for the time plan. And for the final exam, you don't need to, I will not ask you to use answer book. You just write in the place I provided to you. Don't write everywhere, just write in that place I provided. If you write everywhere, there are 20 pages, I need to read every page. Okay, this is for the plan, and no lecture on 1st of November. I will upload announcement to IBLE. No lecture doesn't mean you don't need to study. You just need to work on your project. You just meet the whole group. You guys meet and discuss about your project. Because once you talk to your group member, you know how to work. And of course, during the next 5 lecture time, I will show you a flow chart how to solve those questions. No problem. Okay, we start lecture. For the last lecture, we finish until HMQC. HMQC, we recall some information. For we talked about cozy. That tells you which proton coupled to which proton. In a very, very visible way. You saw a cross peak, you can tell those 2 protons talk to each other. Then we talk about toxi. For toxi, you just need to know there is a technique that can help you to identify all the spins in the same spin system. That's it. So simple. You don't need to memorize anything. Just this. Then we talk about HMQC. After cozy, you know which proton coupled to which one. Now the next question you will find, okay, on which carbon is this proton signal sit on? Then that is HMQC. This is one example. HMQC, they have 2 dimensions. One dimension is proton chemical shift. That's one frequency. The other one is carbon chemical shift dimension. It's another frequency for carbon. Then you don't have diagonal line as cozy spectrum. You have spots. One spot, it goes to one dimension, corresponds to the chemical shift of a proton. And in the other dimension, it corresponding to one chemical shift of carbon. So with one spot, you can tell which 2 nucleus, like proton and carbon, they talk to each other. For HMQC, when they give one proton and a carbon give a cross peak, that means that proton is on that carbon. Very, very clear. This is HMQC. One thing about HMQC is you can readily find distereotopic proton pairs. In that case, you have two proton signals corresponding to the same carbon, like this. This 5,5 prime is a distereotopic proton pair because you can see these two proton signals corresponding to one carbon. Right? For 3,3 prime, you can see this two corresponding to one carbon signal. That means that two protons on the same carbon. But sometimes for terminal CH2 double bond, those two signals, these two protons, they are not distereotopic protons, but they are still on the same carbon. You can clearly see this two, 8 prime. Here, they goes to carbon 8. Now this is two technique we are very familiar with. One is COSY, and the other one is HMQC. Now for these two, you can readily do assignment. But is all this enough? Now we will see with COSY, proton and carbon NMR, are this technique enough to find a structure for an unknown compound? Now we look at this spectrum. This is the proton NMR of one organic compound with the formula of C10H12O2. This is a proton NMR. This is carbon and DEPT. First, we look at the proton. This is zoom in signal. This is overall signal. Now we can see from the integration line, you can see this is one. This is one proton, one proton. This is one. This is one. Also, this is one. This one more or less like 3 protons. This will be about 4 protons because it's higher than this. It's 4 protons. Now, also even though we don't care about the chemical shift anymore with 2D NMR, but it's better. You know in which region you expect what type of protons. For example, for this one, the first thing you can identify is there is this signal with a high chemical shift or above 7 ppm. 4 protons. 4 protons about 7 ppm, you can tell it may be a di-substituted phenyl ring, right? But sometimes you may think differently. 4 protons, maybe it's a pyridine, monosubstituted pyridine, right? Di-substituted phenyl, you have 4 sp2ch, right? For monosubstituted pyridine, you could also have 4 sp2ch. I want to emphasize this again because for some exercise you may have this encounter this situation. You have 4 sp2ch, you always stick to phenyl ring, for sure you will get it wrong because you need to have an open mind. Sometimes like 5 sp2ch, it may be monosubstituted phenyl ring, right? Or a pyridine. For pyridine, it's very clear that's not substituted at all. But for 4 sp2ch, it may be di-substituted phenyl. For sp2ch, you may have a di-substituted phenyl, right? Or you have a mono substituted pyridine. right? You have a 5. You have a 4, right? Now, if you have a 3 sp2ch, how many possibilities you can have? Think about that. I will list a few for you. 1, it can be a tri-substituted phenyl, right? This is one thing. The other one is it can be di-substituted pyridine. This is one possibility. The third possibility, it will be mono substituted sulfin or furan, right? Or this. There is a fourth possibility. Anybody can come up with? There are another 2 possibilities. You can have mono-substituted pyrazine or pyrimidine. For those, whenever you saw sp2ch, don't stick to phenyl ring. It can be heteroarenes. Once in one tutorial, they have 3 sp2ch. Actually, it's a sulfin, monosubstitute sulfin. They always a tri-substitute phenyl. In that case, you get something wrong. That's why there are so many possibilities. Once you have a pyridine, there is one thing you need to that can remind you. Because for monosubstitute pyridine, for example, they may have, if they have only 1 nitrogen, they have order molecule weight, right? You need to always link those knowledge together. For the, of course, for those heteroareal substitute one, it's a high risk to set a question on those in the final, because some students, they gotta stick to the phenyl. I don't want you to lose 40 points just because of this. Just normal questions. Like this is just letting you know, whenever you see 4 sp2ch, don't stick to disubstitute phenyl. It can be a mono substitute pyridine, right? This, I hope, though, with those, I can, you can think about this whenever you see sp2ch. Now for this one, there are 4 sp2ch, and you see here, except oxygen, there is no heteroatoms, right? If you have a furan like those, it can only has 4 sp2ch. In that case, it's not a substituted one. Then you have C4H4O. It's far away from this. That means, in this case, for sure, you have a disubstituted phenyl ring. For this area, you can check how that looks like, right? This one is a doublet. This is a doublet. In the middle, it looks like triplet or doublet of doublet, something like that. At least you see there are 2 doublets there. That can clearly tell you is 1,2 disubstituted phenyl, right? 1,2 disubstituted phenyl. You have 2 doublets. Oh, sorry, 1,2. This one and this one, it's a doublet, right? That's why now it's 1,4-disubstituted phenyl. Then you see, we analyze again. This one will be a doublet. This one will be maybe multiplets. You write it just as a multiplets. This one will be a doublet of a doublet, doublet of a doublet. Then there is one singlet. Okay, that's all. This is the proton we analyze. That's what the information we can get. Now we look at the DEPT. For the DEPT, you see there are 1, 2, 3, 4, 5. DEPT 90 always list on the top. This one you can only see CH. In this case, it has 5 CH. Oh, 4, because here you see there are 2. Here you have a 4. This area you have 4 CH is corresponding to this area. You have 4 sp2 CH. Then you have 2 more CH. In total, you have 6 CH. Then for DEPT 135, you can see they will tell you how many CH3 and CH together. Now in total, you have 7 signals minus 6 CH. You have 1 CH3. Now you have 1 peak face down, that's CH2. Again, you use carbon minus all the signals from 135. You have a quaternary carbon. Now you see here, you have 1 quaternary carbon here. 2. You have 2 here. Now this is all the carbon. The carbon you have 6, 1, 1 plus 2. In total you have 10. It match. Now for protons you can see 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 here you have 4. You have 3. 1, 2, 3, 4, 5, 6. You have 9. 9 plus this singlet. That's 3 protons. You have 12 protons. That match. Actually, when you look at this, you have 1 singlet with 3 protons around 3.5. You can tell it's a methoxy. Because here you can see you have 1 methyl group here. Then this is the analysis of the multiplets of the proton. In total, you can get 3 structures like this. It can match this part. Based on those, we draw 3 structures. This one we will analyze all these proton signals. For examples, if it's the first structure, then here is a chiral center, here is a chiral center. Now you will see this is the distereotopic protons. Now for this one, it will couple to 2 protons, 2 distereotopic protons, couple to each one, give a doublet. Now this one will be a doublet of doublet, the same as this one, doublet of doublet. For this, the middle CH2, each one will be a doublet of doublet of doublet because they couple to themselves. They also couple to this one, also couple to this one. They will be a doublet of doublet of doublet or a multiplet. This is for one. Does it match? You don't have any doublet, right? You have doublet, doublet, or a multiplet. Doublet, doublet, multiplets. Then you don't have this doublet. That's why that's not possible for the first one, right? Now we look at this. Now this one is one chiral center, another chiral center. This proton will couple to this one, only couple to this one, give a doublet, right? Now for this one, it will couple to this one, give 1 doublet. Now this is a distereotopic CH2. Then they couple to 2 of this, will give 3 doublets or a multiplet. Now for this distereotopic pair, they will couple to themselves, give 1 doublet, and couple to this one, give another doublet. Now you have a doublet of doublet. As this is 2 protons, you have 2 doublets. one doublet, two doublet of doublet, one doublet, one multiplet, or doublet of doublet of doublet. In that case, this case, you have two doublets here, one doublet, or two doublet of doublet, those two. You have one doublet is here, and in the middle one, you have a multiplet or 3D, right? This one match. The same, you analyze this one, and this you just change the method of position. It doesn't affect this part, right? This also match. Now you see those two match. Then this is the cozy spectrum, and you can see for 1, 1, or here 1, 1, those 1, 1, they couple to each other, right? Here. This is the cozy spectrum. Diagonal line, you know, this is 1, 1 prime, they couple to each other. Here it's like this. They will couple to 2 here, 1 or 1 prime couple to here is 2, this is 2. You see, we analyze from this way. Now 2, 3, they couple to each other. Here, 2, 3, they couple to each other, give 1, right? Now you have 2 couple to 1, 1 couple to 1, and 2 couple to 1 prime. You have all this that match. Because this, as we analyze the multiplets already, and the cozy, actually it doesn't, it's not that important anymore. Unless we cannot, from multiplets, we cannot see which couple to which. Cozy helps. But in this case, we can clearly analyze the multiplets. The cozy is not so important anymore, right? Now this is HMQC. You see, 1, 1 prime, you see those two corresponding to 1 carbon. This is the distereotopic proton pair. And this CH3, here it goes to this signal. Proton 2 here, it goes to carbon 2. Proton 3 here, it goes to carbon 3. Now for this part, we don't need to sign, because this one, we want to find the structure. This is to assign this part is not so important anymore. Now we have two structures, they fit. In that case, we want to find out how this, for those spectrum, this proton, this carbon, we need to pick up 1. But now both fits. This is, with the technique we have now, we cannot tell which compound of these two have this spectrum, right? Now we want to find out which one. In this case, cozy, HMQC cannot distinguish those two. Now we need another technique. This is HMBC. HMBC is very, very useful technique to find connectivity, because it tells J2, J3 what 2-bond or 3-bond correlation. It can, like here, this proton, this CH, this proton can see this carbon, can also see this carbon. Now, this proton, the same, this carbonyl carbon, this they can also see the same as this. Even there is heteroatoms, they just count the bond. They don't count heteroatoms. In that case, this proton, they can also see this carbonyl. Right? This is HMBC. They show 2-bond and a 3-bond. Because once you see, you can see further, you can find more connectivity. Now, one apply this technique. This is also a proton-carbon correlation. They also detect proton. That's why this one is pretty easy to conduct. Now we analyze for those two structures. The only difference is methoxy group. Methyl on this oxygen or on this oxygen. Now we analyze if the methyl is on this oxygen. Now this purple proton, one bond will see this carbon. Two bond oxygen. Oxygen is not animal active, forget about this. Three bond, it will see carbon 2. Right? One bond, two bond, three bond will see carbon 2. If it's the top structure, the methyl group will show correlation with carbon 2. Right? 2 bond away, 3 bond away. If this is the bottom structure, this methyl group will 1 bond, 2 bond, 3 bond. Like 1 bond, 2 bond, 3 bond, see carbon 3. Now you see, if we have HMBC spectra for those compounds, we can tell which compound have this spectrum. If it's a top structure, this purple promethyl proton will see carbon 2. If that's bottom one, this purple proton or methyl will see carbon 3. Here is the HMBC. Methyl group is here. You just draw one line down. Methyl, one line down. You will see methyl proton and carbon 3 have a correlation here. Very clearly, with carbon 3, they have correlation. With carbon 2, they don't have any correlation. That means methyl proton show correlation with carbon 3. Now it's clear. It's this structure. Methyl see carbon 3, not carbon 2. If methyl see carbon 2, it's this structure. Methyl see carbon 3, it's this structure. Now with this HMBC, we can clearly tell it's the bottom structure. Right? Now you see for HMBC, it is very important to see connectivity. Once you give a fragment together, you want to put fragments together. If you only see one bond away, you don't know what's away after one bond. It's difficult to connect the fragments together, right? If you can see 2 bond or 3 bond, in that case, that can help you. Now by this, I want you to know the difference between HMQC, HMBC. HMQC, the proton can only see the carbon where the proton located. But for HMBC, it cannot see the carbon where it's the proton located, but it can see 2 bond and 3 bond. As I mentioned last time, if you don't know how to find which peak the proton can see, you just assume yourself is a proton. You sit on one carbon, you look around, not look down on your feet. If you only look down on your feet, you can see which carbon you are on. In that case, that's HMQC. If you look around, of course, if you are a proton, you sit on a carbon, you stand on the carbon, you only see 3 directions. Because yourself have a bond to carbon already, they have another 3 bond for sp3 carbon, right? You see another 2 bond or 3 bond away. You can see 2 more carbons or 2 more atoms connect with the carbon the proton is on. Now this is HMBC. From this very simple example, you see how powerful the HMBC is. Normally, HMBC is the last step, last technique you use to put up the fragments together. Okay, this is for the part. We will spend more time on HMBC because it's very important. Then we will focus on HMBC for some time. In this is HM. This is the summary of HMQC. Then this HMQC or HSQC, just to recall, and it can help you to assign the carbon signals. You guys are familiar with this spectrum, right? It's the tutorial questions. Last time with COSY, we can assign 2, 4, 3 with certainty. Now this is the carbon signal. This is the proton signal. After we assign all the proton signals with HSQC, we can readily assign all the carbon signals. Now you see this is the assignment of the proton signal, but then 7, proton 7, it corresponding to this, right? Now this one, proton 7, is this place, right? Now you see this signal is this carbon, right? If you see signal, this signal is assigned to proton 1, it's here, proton 1, draw a line here, we just from the top, okay, from this one. This is a proton 8. This is methyl group. It shows correlation to this carbon. That means this carbon signal is this carbon. Proton carbon is on carbon, proton 8 is on carbon 8. They show one correlation. This is HMBC peak. They say is HSQC the same. HSQC and HMQC, they are the same. Here, this cross peak tells you this proton 8 corresponding to carbon 8. Now you see this proton is here, now this carbon is here. Now for this one, this is proton 3. They show correlation here. From this cross peak, you can find carbon 3 is this signal. Now this is proton 4 is here. There is a cross peak here. You will find carbon 4 is this signal. Now this is a proton signal 2. It shows correlation here. Proton 2 is here. That means by this cross peak you will find carbon signal of this CH2 is here. Now this is 5 is here. This CH2 proton signal is here. By you draw one horizontal line, you find, okay, this carbon signal is this one below. And then this is signal 1 here, CH2 here. It corresponding to this one. That means this carbon is here. 7 we analyzed already. 7, this CH2 is here. Now after we use COSY to analyze all these proton signals with HSQC or HMBC, we assign all these carbon signals. In that case, where is carbon 6? With this? Yes. Because for HSQC or HMQC, they detect proton. After they detect the proton, they can find carbon. But for carbon 6, here is a carbonyl. There is no proton on it. That's why you cannot find the carbon signal of carbon 6 in the HSQC. HSQC, they can only help you to identify carbon with proton on it. Okay, this is HSQC or HMQC, but now it's very important time I want you to know. With 1D DEPT, you can tell which signal is CH2, which signal is CH, which signal is CH2. CH, CH2, CH3, right? That's DEPT. Because in that case, you need to know DEPT 90, you find CH face up. For DPT135 with CH, CH3 face up, CH2 face down. You need to remember this. Otherwise, you cannot identify which one is which. But with HSQC or HMQC with this one, you don't need to remember which one is face up, which one is face down. You can still identify which one is CH, which one is CH3, which one is CH2. Now we can see by integration. You see here? With the integration, you can clearly tell this is 2 proton, 2 proton, 2 proton, 2 proton, 2 proton, 2 proton. This is 3 proton, right? Now this one is 2, 2, 2, 2, 2, 2, 3 protons. By this, you can tell this 2 proton is on this carbon. That means this carbon is a CH2. The same, this one corresponding to here, this one is also a CH2. This is a CH2 again. 2, 3, 4 is here. They are also CH2. Now for signal 8, it's a CH3 because you know that by integration, you know this is 3 protons on the same carbon. They are CH3. You see, by integration and this carbon signal, you can tell which carbon is CH2, CH, or CH3, right? The one that you didn't observe in the HSQC is a quaternary carbon. The same with HSQC, you don't need to remember face up or face down. Just by integration, you can tell CH, CH2, CH3. That's why I say 2D NMR is easier than 1D. For 1D, for DPT, you need to conduct DPT90 or DPT135, 2 experiments to tell CH, CH2, CH3. But with HSQC or HMQC, 1 experiment, you just do integration. You will find out CH, CH2, or CH3. You don't need to remember face down or face up. You just look at the integration and this you know. Now you see you can remember less, but you get the same information. This is one thing, but I want to remind you. For 2D NMR, when you record, you will see it's a color printing, red and black. For red means negative, for black means positive. From this, maybe you can tell it's kind of a DPT90, DPT135. CH, CH3, face up is positive, black. CH2, negative. Face down, negative, red. This one just let you know from HSQC, from the color of if the spectra is a color printing, you can tell CH2 is plotted in red. CH, CH3 plotted in black. In the carbon 6 is a carbonyl is around 133 is here. You see this signal? You see this one it only goes to 765. This one is 173. It's on 1 floor down, maybe. Right? Now you see how to read the color of the HMQC. CH2, red, CH, CH3, positive color, positive peak is black. Just like DPT 135. CH, CH3 face up, positive, CH2 face down, negative. It's like this. Now again, this is one thing I want you guys to, these examples, we also use examples to introduce HMBC. Like here, for this molecule, you have this one is CH2, ethylene. This is a 2-ethyl group. You know this is this proton coupled together. One is a triplet, one is a quartet. This one is a triplet, this is a quartet, right? For this CH2 together, one side is oxygen, the other side is carbonyl. That means this CH2 only coupled to this CH2. That means this is a triplet, this is another triplet. This is analysis. Now we look at the spectrum. Here you see it is a quartet. This is the triplet, this is the quartet, this is the triplet, this is the 2 quartet. Now we know for the 2-terminal CH3 is here, right? And this 2 quartet is 3.5, about 4, then is the 2 quartet is this and this. Then this is one triplet, this is another triplet, is this one. By analysis, we know this CH2 next to oxygen is this. This one next to carbonyl is this. You know, we don't need 2D anymore. We can presumably sign all this. But if I ask you, okay, we go to the next slide. We will see. This one is a cozy spectrum. Because you can see the diagonal line, this is a proton, diagonal line, that means it's cozy. Cozy means you see, like this is a quartet, this is a triplet. You see this one and this one give a cross peak here. We can only tell it's a CH2 coupled to CH3. Now, like for this one, this is a quartet, this is another triplet. We can tell this quartet and this triplet coupled to each other. That's CH2 coupled to CH3. Now for this middle one is CH2. This is 3 because it's next to oxygen. This is 4. That means this is 3 coupled to 4. Proton 3 coupled to proton 4. Right? You see a cross peak here. With this cozy, we can only tell this is signal 3, this is a signal for proton 4. But for this 2-methyl group, with cozy, we can only tell this one and this one are one set of ethyl group. This one, and this one, the one on the left, they are one set of ethyl. But there are 2 ethyl in this molecule. Which set is which ethyl? We cannot tell, right? Again, also this is HSQC. You can see this CH2 on this carbon, because now 4 is on carbon 4. This is proton 4. You can find the carbon 4, and this is proton 3. Here you can find the carbon 3. This 2, the top one, right? Now about which ethyl, like the red one or the black one, which set belong to which, we cannot tell, right? Again, for this HSQC, you can see this is CH2, you know, CH2 is red, CH3 is black. Now we cannot tell which one is which. If we do analysis, again, using HMBC, we can see, like this, we know we can sign proton 3 and proton 4, right? With HMBC, you can 3 is here, 4 is here. Right? Now, if we want to sign the ethyl group to ethyl group, we need to analyze. Like we look at this ethylene group, this proton, this CH2 of this ethyl, we just give it a number 2. Proton 2, 1 bond will see this carbon, carbon 2. 2 bond will see oxygen. 3 bond will see this carbon, right? We assign, with this we assign carbon 3 already. We assign carbon 4 already. Now proton 2, if we give this a label like this, proton 2 will see carbon 3, the same proton 6 here, 1 bond see this carbon, 2 bond see this oxygen, 3 bond see this carbonyl. Now we can look at carbonyl or this carbon 3. If carbon 3 see proton 2, that means that signal is the proton 2. If the carbonyl C1CH2 can see this, that means this signal will be 6, right? Now we look at 5. This is carbon 5. It's a carbonyl, right? You draw one horizontal line. You will see now for carbon 5, which proton can see carbon 5? 4 can see carbon 5 through 2 bond. 1 bond, 2 bond can see, right? 3, proton 3, 1 bond see this, 2 bond see this, 3 bond see this. Then it means 3, 4 can see 5. Again, 6 can also see 5. If 6 can see 5, carbon 5 can see 6, right? Now if we use 5, you can see 5 can see 3, 5 can see 4, 5 see another one, 5 see another one. That means this cross peak belong to proton 6, right? Because you analyze this proton can see 5, 4 can see 5, 3 can see 5. Now we identify 3 and 4 already. They are here. The only thing left is 6. Proton 6 can see 5. Now this one will be 6. 6 see carbon 5. Then you draw one horizontal line, vertical line. You see this one will be 6. Because 5 and 6 will give a cross peak in HMBC. Now you see this one will be 6. Once you have this is 6, now another methylene group here will be 2, right? You have 6, then from 6 you can find 7 because they are belong to one SO set. Then once you have this is 6, the only thing left is 2, right? 2, from 2 you can see 1 because 1 and 2 they are in the same ethyl set. But this is after we analyze, we find 6, we know the other one is 2. But now we will do analysis on 2. By analysis we will see proton 2 will see carbon 1, right? We will see carbon 3. Now you see, this is proton 2. Here is 1. Here is another one, right? This is HSQC. But now this is this will be the HMBC. You see proton 2. Here they will see 1 here and another. This one will be carbon 3. They will see carbon 3 here. This one on the top one. You know this will be 2 signals from the zoom in. You see 3 here. 3 is on the top, right? Now from here you can see proton 2. You see here is 2 carbon signals. You can see 2 spots. This one is on the top one. Then 2 will see carbon 3. 2 will see carbon 3 here, right? By this now we can analyze all, we assign all this 1, 7, 4, 3, 2, 6. Then from 1, proton 1, or this is 7 signal, it goes, this carbon will be 7. Then this proton 1 here, this signal will be carbon 1. Then proton 2 is here, it corresponding to this. That means the lower part, lower one, will be carbon 2. Then this is 6, proton 6. Then this will be carbon 6. By this, we sign all this carbon. We sign all the proton, all the carbon is here. Because we use HMBC to identify this ethyl from this ethyl. Because this ethylene CH2 can see carbon 3, this ethylene CH2 can see carbonyl 5, right? Here, 6 can see 5. 6 see carbon 5 is a cross peak here. 6 cannot see 3. 3 is the one on the top. 6, this area, there is no correlation. That means 6, this proton, this ethylene signal, CH2, see carbon 5, not carbon 3. That means this signal is this. This is for the HMBC. In the first few examples, you may have difficulty to identify, and later with more examples, you can clearly tell how useful it is. We have a 5 minutes break, and we continue.
This one is C4 change to C6, then this one C6 change to C4. Oh, okay.
Stop catching in your lead.